Okay, we're continuing on with page 3, question 5. So Xavier, Yolanda, and Zeke are all trying to find a line of best fit for data they collected together. Below are the graphs each student created using the same scatter plot. So the scatter plots were all the same, and they're just imposing their lines of best fit. And just says comment on the success or failure of each person's attempt. And in class, I think you guys did a great job of describing the situation here, right? Xavier's issue here is that this is not really describing this this situation, right? His line of best fit is clearly below nearly all of the data points. Now, I believe that what he did was he probably selected, this point, and he selected this point, and he used those to create the equation of the line that fit the data. So there's no attempt to use a least square regression line or find that. This is just basically he's picking a couple points and saying, hey, what's the line that fits it? This is the one he picked, and I think it's problematic because it's clearly not describing the data set. It's definitely always making predictions that are lower than what's really happening in the data. The next one here is Yolanda's, and I find this one, I think I find it better. I'm trying to think of some of the things that you guys said in class. It feels like there's 1, 2, 3, 4 points below, 3 points above. So I don't think this is necessarily a bad line of fit, but yeah, I don't know. I think this does a good job of describing the data. I just think that when I look at this scatter plot, it seems like Zeke's graph does probably the best of the three job of describing the data. One of the things I noticed is that he's got 1, 2, 3 data points that look like they have no residual. He's got like roughly 1, maybe even 4, right? He's got a couple above rather, and like 3 below. So it just feels like it's kind of doing an overall, maybe slightly better job of fitting the data. I would be interested to find the least square regression line, and then just kind of compare the slope and y-intercepts with these three. But I would say Xavier's probably, this is a failure, right? This is not a good line of fit. Yolanda's is a moderately good line of fit, and I think Zeke probably nailed it. Perhaps Zeke even plugged these values into a calculator. This was the least square regression line. So let's move on now to question number 6. Question 6 says, what is the equation that represents the table of values at the right? So here's a table of values, and this is just having us go from one representation of a data to another. As I look at it, I can see that there's something happening here from 6 to 24, and from 24 to 96 that is I think I'm comfortable with in terms of arithmetic. I am going to grab my calculator and take a look at it though. So let's take a look at, for example, 24. This is silly. 24 divided by 6, and we would be shocked if we didn't get it, but we did get 4. So 6 times 4 is 24. Now if I take the 24 and I multiply times 4 again, times 4 again. Jeez, I missed the multiplication. Times, is it not working? Times 4 again. When I do that, I get 96. So at least in these two instances, I'm multiplying by 4. Now I can go backwards and check it, right? I can take 6, and I can divide by 4. And when I do that, I do get 1.5, and I can divide that by 4. When I do that, I do get 0.375, and I can divide that by 4, and I get... Okay, so it's pretty clear what's going on here, right? I have a multiplier of 4. So when I have a relationship like this, where these values are increasing by 1, and these have a common ratio, right? It's a common ratio, meaning it's the same ratio of 4 each time, right? It's pretty clear what's happening here. This is an exponential curve. And to write the equation that models it, this is a very helpful value, right? That's my 0th term, and I could just write y equals my 0th term, which is, not 5, but 1.5. and I'm just multiplying that each time times the number 4. And to show the repeated multiplication, I'm just going to write it up to the exponent of x. Now this is the explicit equation for this situation. If I wanted to write the recursive rule, I could say something like this. I could say I could use this term. I could say the 0th term of this sequence is the number 1.5. Or I could even say this. I could say the first term of the sequence is 6. That looks maybe better. And then I can write, in order to get to the next term in the sequence, right, take the term that you're at and multiply by the number 4. So these two together, and again, look at this. What is this saying? In order to get to another term, take the term that you know, and then what do you do with it? You multiply by 4. And the reason why I read this like this, right, the next term, the n+1 term, take the nth term. If I pick any value for n, like if I say, okay, if n is 1, then this would be n is 1 plus 1, or 2. So this says, hey, to get the second term, take the first term and multiply by 4. Well, conveniently, I know what the first term is. It's 6, right? So instead of doing it for particular values of n, I just say, hey, in order to move forward in general, what do? You take the term that you're at, multiply by 4, and you can move forward. So that's how the 6 becomes the number 24, and 24 becomes the number 96, just by repeated multiplication of 4. So that is question number, what was that, 3? No, 6. Oops. Next, we've got Ed, but not Ed, and Eddie. So Ed can paint a garage in 6 hours, while it takes Eddie 8 hours to paint the same garage. How long will it take the two of them together? So this is not necessarily how we first started talking about these, right? We tried to do a lot more looking at the units and trying to think very clearly what's happening. But we're trying to do one job. This pen is too thin. Let me bump this up here. We're trying to do one job, right? One job, and the job, it doesn't really matter what it is. The job here is to paint a garage, right? Paint a garage. And we're just talking about that's the one job. And this guy Ed can do that one job in 6 of the hours, right? So when I look at this 1/6 is the part of the job that he can do in one hour. If I want to express this as a unit rate, right? He can do 1/6 of the job per hour. Now, that's the rate he can accomplish this job at. Now, if I combine that rate with the rate that Eddie can contribute to this, right? Then I could ask the question, well, how fast can they do this one job together? So Eddie, his rate is he can do this one job in 8 hours. So that's me combining the rate of Ed plus the rate of Eddie, and the question is, what do I get when I combine those rates? So with these rates combined, I'm going to get the amount of time. Well, actually, they could do the one job in X number of hours. So our goal here is just to figure out what X is. And when I looked at this, I always like to use fraction busters when I have an equation to just multiply through by a set of factors that'll completely eliminate any and all fractions at all. And I could do what 6 times 8 is 48. I could do the 48, but if I just observe that 6 is the number 2 times 3 and 8 is 2 times 2 times 3, right? The smallest value that I could get away with multiplying it by, 8 is 2 times 2 times 2. I need 3 factors of 2, and I need a factor of 3. So I could go with 3 times 8, or 24. So I could clear all of these fractions by multiplying both sides of this by 24x. So again, big idea, and I can't stress this enough, is just the fact that I can push through factors of 24x to every single term on both sides of the statement. Each one of these is going to pick up new factors of 24x. Now, I don't need to write those all down. I'm just going to simplify them kind of mentally here. But if I've got 24x divided by 6, that's going to become just 4x's, right? So this is going to become 4x. And then plus 24x times 1 over 8. 24 divided by 8 is 3, so that's just become 3x. And then that's going to equal 1 over x times 24x. There my x value is eliminated. I'm just left with the number 24. So this equation becomes 7x equals 24. And if I solve that for x, right, x is 24/7. So they could do the job in 24/7 of an hour. And I like some of you were converting this into not only hours, but you were doing hours and minutes. And I thought that was super cool. And I don't know, I might ask that on a question. So on a test. So when I do this, I get 3.43 hours. So I know it's 3 hours and some number of minutes. Not 43 minutes, for heaven's sakes. It's 43/100ths of an hour. So one of the things I could do is I could look, I've got 0.43 hours, and I want to convert that into minutes. So to do that, I can multiply by a giant 1. And I want hours to be in my denominator, so they're eliminated. And my numerator I want to be minutes. And to make this actually the number 1, right, the relationship here is that there are 60 minutes in 1 hour. So now this is truly the number 1. So I'm just taking 0.43 hours and I'm multiplying it by the number 1. And it's number 1 because of the units that are attached with the numerator and denominator. And of course, if I multiply something by the number 1, I don't change its value, what its quantity is. I'm just changing the units of it, or I'm changing the form that it's in. So if I just multiply 0.43 times 60, I get that this is going to be 25.8. So this becomes 25.8. And now notice that my hour units are gone, and the thing I'm left with here are just minutes, right? So this is a number of minutes, 25.8 minutes. And if I wanted to, I could go another step further, and I could say, hey, let's turn these into seconds. But I think I'll stop here. And I'm very happy with this answer. I did not say convert this into hours and minutes. But that dimensional analysis piece is just really important, and it's nice that it showed up there. Last question here on this page is a very similar question. In fact, so similar, I probably should have deleted one of these. So, 180 complete a beginning level Sudoku puzzle in 24 minutes. Oh, this is slightly different, actually. Daryl has never tried a Sudoku, but is willing to work with Juanita on a beginning level Sudoku puzzle, the one that she can do in 24 minutes. Together, it takes them 14.4 minutes to solve it. How long would it have taken Daryl to solve the same puzzle alone? Show your work. Well, I think we're making some assumptions here, right? About maybe Daryl's getting in the way and slowing Juanita down. I don't know, but let's just go ahead and go with this as a standard work problem, anyways. So we know that they can do the one job. And you're like, what's the job? Well, the job is they can solve one of these puzzles, right? They can do one puzzle, P-U-Z-Z-L-E, in a total of, let's see, together they can do it in 14.4 minutes. So that's their combined rate. They can do one in 14.4 minutes. Now, alone, Juanita can do one of these puzzles in 24 minutes. And I'm assuming that Daryl added something to this, right? He can do the one puzzle in, well, we don't know how many minutes. I'll just say X minutes. So the question here is, what value of X, right? He can do the puzzle in what part of it can he do in the one in X minutes? So we just need to solve this for X. So I'm going to multiply. You know, I'm not going to do any multiplication. I'm just going to symbolically think about it. I'm intending to multiply both sides by the number 24 and 14.4 and x. So I'm going to push through those three factors across this entire equation. For the very first term, right, 24 times 14.4 times x divided by this 24 is going to leave me with 14.4x. So I've got 14.4x plus, when I take the 24 times 14.4 times x and I divide it by this x, that's going to leave me with this product, right? 24 times 14.4. I'll leave it at that. It's 24 times 14.4. And then finally, on the other side of this, I'm going to divide everything by 14.4. When I do that, I get this is 24x. Okay, so in order to solve this, I guess I'm going to take away. I'll just subtract 14.4x from both sides. So when I do that, on this side, I'm going to get simply 9.6x. And then I'll multiply 24 times 14.4, and when I do that on my calculator, I got 345.6. So to solve this for x, let me take the 345.6 and divide it by 9.6, and I get 36. So x is 36. So I believe that let's see, Darnell should be able to solve in about 36 minutes, MIN. So I wrote that down, and the room is kind of crowded there, but I want to just, remind you that it's really nice when you do a problem that you put your solution back in kind of terms of the original problem. So x is 36 is like, what's x, right? What are we talking about here? Daryl should be able to solve this problem in about 36 minutes. It's a nice answer. I didn't do this up here, but together they should be able to paint the house in 3.43 hours, or 3 hours and 25.8 minutes, right? So just remember to do that. It's a courtesy to the people who are reading it, and it really communicates exactly what you're talking about.